I will begin with a word of prayer. Dear Father, we thank you for this day. Again, Lord, I thank you for the students, and I just pray that we would use this time wisely and that you would protect the students not here, that they would have good travels and come back safely, Lord. In your name I pray. Amen. All right. So let me, I have potentially an example. I've been searching for a more interesting example. I don't think this is the most interesting example, but it's an example. So, example of pullbacks and such. So what I want to do is I want to look at the function f that, let's say, goes from oh man. Well, I don't know. I guess I'll write it this way. 0 to infinity included. No. Oh man, I'm sorry. All of a sudden my example just went to... I'm sorry, guys. All right, let's try that again. R3 to R4. I think that'll do it. And so here I'll use U, V, W, and over here I'll use X, Y, O, X, Y, Z, and let's say T. All right. And my map is going to be F of U, comma, V, comma, W equals to, all right, here goes nothing. U cosine V, U sine V, and then W, W. So I believe, I mean, one way you could look at this is F is a parameterization of a three-dimensional manifold which is embedded in R4. So then we can look at various differential forms and try to pull them back under F. Or we could try to push forward vector fields in the domain if we wanted, right? So let's try to look at the pullback of something. Like let's look at the pullback of, let's try to pull back dx dy. Right. So as we discussed last time, I mean, we could be overly formal with the definition and everything, but the theorems, which shortly worked out afterwards, basically show that you can take this and this and this and this and plug them in and so calculate. So in other words, this is really the differential of the pullback of the x function wedged with the pullback of the y function, which is meaning substitution. So that's the differential of u cosine v wedged with the differential of u sine v. And then we can work that out, right? So that's like cosine v du minus u sine v dv wedged with sine v du plus cosine, well, plus u cosine v dv. What's that work out to? So this guy and that guy gives me a u cosine squared. This and this give me, after I anti-commute the wedges, minus u sine squared. So I get sine squared plus cosine squared. I just get a u du wedge dv. So there you go. That's the pullback of the dx wedge dy form. All right.
So this is like basically using the theorem that Ignorant has at the end of that section
Right, that we can calculate pullbacks by substitution. We can also, there's also a larger idea here, which is like, I'll be looking at differential forms which are in some sense on R4, but I'm really restricting them to the image of this map. That'll become more apparent in my next example here. So like, how about if I look at the pullback F, and we'll do a single one. How about F pullback of dz plus dt? Or we could just look at, how about this? Maybe less weird. Pullback of dz is the differential of the formula for z pulled back, which is what? Right. W. Okay, that was not a long calculation. Okay. What's the pullback of dt? Same song and dance, right? So there's some kind of interesting things that go on here, right? Like, if we look at the pullback of dz plus dt, what happens? By the way, the pullback is linear, so the pullback of a sum is the sum of the pullbacks. So we can just add the previous two calculations, and we get 2 dw, right? On the other hand, if we looked at the pullback of the difference of dz and dt, what would that give us? 0. Yeah, that would give us 0. Why is that? What's the difference between dz plus dt and dz minus dt, like geometrically? Do you understand what's going on here? What if we tried to rewrite this? So I'm thinking of this as being, say, a manifold M, which is some subset of R4, right? So I've captured it, this geometric set, as a parameterized manifold at the moment. But perhaps it would be interesting to rewrite it as an equation, right? So we're looking at a three-dimensional, what? Is it three-dimensional? Yeah. Let's see here. I mean, can I write? I guess I have. You know what I was thinking originally, guys, was whenever Dunkin' Donuts, because I canceled calc too early because with 5 people, why should I meet the whole time, right? And so. Tried to get some coffee, and on the way back I was thinking of this example, and in my thought I didn't want the u here. When I don't have the u here, then it's a two-dimensional manifold. But I wrote what I wrote, so we can deal. But the point is, if we look at x squared plus y squared, if I didn't have the u there, then this would be 1. So we'd have the equation x squared plus y squared equals to 1, but I didn't do that. So all I get is x squared plus y squared is equal to u squared, which isn't an equation. It's just an admission that x squared plus y squared can be pretty much anything, right? So there really is no particular restriction that I see. I mean, can you see a restriction for the x and y piece? I don't think so. I mean, this is a three-dimensional manifold, right? We have to check the Jacobian to be sure, but I think that has, we can calculate, well, here we can be sure in a second by, if we can find a non-trivial 3 form on M which pulls back, that will prove it's three-dimensional. You can't have a non-trivial 3 form on a two-dimensional space, among other things. But anyway, what I was getting to here, so the equation for M is really dumb. What's the equation? M is what? It is the set of points x, y, z, t, such that what? Yeah, z equals t. There you go. That's it. So it's not especially surprising that since z minus t is equal to 0 on M, that says that the differential of z minus t is equal to 0. In other words, dz minus dt is 0 on this space. On M, this is, so, you know, in 4 dimensions, the differentials dx, dy, dz, dt, these are independent, right? But if you restrict those to this three-dimensional manifold, then there can be a relation between the differentials. There may not be. It depends on the interrelation between the coordinates. Right? I don't think you can find a relation between the x and y differentials restricted to M. I think if you look at dx and dy restricted to M, well, look at here. I mean, maybe this shows you exactly what to think about. If we think about x and y restricted to M and we pull it back, we get this, right? So this says to me that x and y are going to be independent unless what? We're along the part of M which is coming from u equals to 0. Right? So along the u equals 0 part of M, I could not use x and y as independent coordinates, because the pullback of the wedge product of dx and dy is not 0, is 0, which speaks to a dependence between dx and dy. Yeah.
When you say d equals to t, is that because they're both equal to w?
Yes. Exactly. What would like the pullback of dx? I mean, how about this? Pullback of dx wedge dy wedge dz would be what? The way it works is beautiful, or to quote Matthew, booful. I forget what I did. I did something yesterday, and Matthew's like, "Daddy, that's booful." What was it? It was something mundane, but he really liked the way something looked. I don't know. When Daniel was younger, he used to arrange his food in patterns. It was kind of cool. He stopped doing that lately, but. So this, we already calculated. It was u du wedge dv, right? And the pullback of dz was dw. So this suggests to me that I can use x, y, z as coordinates on M, provided I stay away from the part of M, which is coming from mapping of which is the part mapping from u equal to 0. So this is a problem on a manifold is what can you use as coordinates, right? And so we might have to use different coordinates on different pieces. Long story short. Now, if I throw out the u, if I just have cosine v and sine v, that would give me a two-dimensional manifold inside R4, and then I wouldn't be able to find a 3 form. No matter how I pulled back 3 things, I would end up with a duplication of like the u and the v, or I guess the u and the w if I get rid of the v and the w if I get rid of the u. But I don't know. Is this at all helpful?
Yes.
Okay. This is something we'll keep chipping away at this whole semester, though, is like, what is the pullback for? I guess the other question is, there's 2 questions, like, what's the pullback for, and what are differential forms for? I mean, to me, what they're for, in some sense, is detecting the existence of certain objects reveals structure in the manifold. Like the existence of these non-trivial 3 forms to me says, hey, it's 3-dimensional at least. Could be more. It isn't, but all right. So there's that. Now I think I have an example that I can work out for you guys that you might enjoy. See if it works. We'll try it out. So here's the problem. Ooh, I should save this one for your homework. That one's too complicated. Let's see here. This one's nice. Kind of. That one I talked about already. I'm going to talk about this. I'll probably regret this. Alpha equals to x dy wedge dz minus y dx wedge dz plus z dx wedge dy, all divided by the x squared plus y squared plus z squared to the 3/2 function. This would be a 2 form, all right, a 2 form on R3 with the origin removed. Okay? And so we're asked to do 3 things. Number 1, prove that alpha is a closed differential form. Number 2, compute the integral over the 2-sphere of alpha. And number 3, answer how does this prove that alpha is not exact? What is it? Oh, okay. Well, we'll get back to it. So the first one is actually the most fun, but also the one I probably shouldn't even do. But if you calculate d alpha, what happens? If we were going to show that it's closed, what would that be? That would be, you'd have dx, right? Oh, it's worse than that. It's d of x over that. Let's call that thing rho cubed wedge dy wedge dz minus the differential of y over rho cubed dx wedge dz plus the differential of z over rho cubed wedge dx wedge dy. So rho is the square root of x squared plus y squared plus z squared, right? So like what's partial rho partial x? It is in fact x over rho. Very good. So what does that make partial x over rho cubed equal to? Likewise for curses. Oh. Sorry, I'll behave. Oh, wait a minute. So in principle, this has a dy and a dz term as well, right? This has a dy and dz term and a dx term. This has a dy, dx, dz term. That has a dy, dx, dz term. But we only need to calculate the x piece, the y piece, the z piece, because everything else wedges to 0. So that's simplifying. So if I think about partial x of x over rho cubed, what does that give me? That gives me rho cubed minus x times 3 rho squared times x over rho divided by rho to the 6th by the quotient rule, which simplifies to what? Rho cubed minus 3 rho x squared, right? Divided by rho to the 6th, which is actually what? Rho squared minus 3x squared divided by rho to the 5th. So what you got here is a rho squared minus 3x squared over rho to the fifth dx wedge dy wedge dz minus rho squared minus 3y squared over rho to the fifth dy wedge dx wedge dz plus rho squared minus 3z squared over rho to the fifth dz wedge dx wedge dy. I do not know why I'm expending so much mental energy to do this right now. It's really foolish on my part. There's far more interesting things for us to talk about today. But every once in a while, it's fun to do a calculation. So you'll forgive me, I guess, or not. Do you guys agree so far? I mean, it's this quotient rule and then what happens? We got dx wedge dy wedge dz. This one, I have to flip the x and the y, so that turns this minus into a plus. And this one, I have to move z 2 spots, so it keeps plus. So I again end up with a 3 rho squared minus 3x squared minus 3y squared minus 3z squared divided by rho to the fifth dx wedge dy wedge dz. Which is 0. Because that's 3 rho squared minus 3 rho squared. And so there you have it. I should have made this a homework problem, right? Oh well, too late. Oh, I do? Oh. You know, you'd think I'd remember that. I made that homework up like not that long ago. But goodness gracious, what's wrong? Anyway, so you know what this is? This alpha, it is the work form of the force field F, where the force field is equal to what I usually call r vector divided by r cubed. It's the Coulomb field. This actually is the Coulomb field written as a differential form, 2 form. Yeah.
I think you messed up the signs because it's minus in the middle term.
Well, but the thing is, I have to change that to this.
Oh, that's true.
See, and you notice over here I did something else. I moved this guy over there, but that minus minus gave me a plus. So they're yeah. And this minus in the middle is because the flux form correspondence rather flux form. 2 form, right? Flux form. This is the flux form. This is the flux form corresponding to the Coulomb field. The radial, spherically symmetric, magnitude inversely proportional to the distance from the origin field, the Coulomb field. And as you can see, so this is the differential form version of showing that the curl of that vector field is 0. Wait a minute. The divergence, it's pretty obvious what we're calculating is a divergence, right? That's like partial E, the x derivative, the y derivative, the z derivative added together. This is the divergence calculation, the divergence of the Coulomb field 0. Yeah. Okay. Yes, yes. So now part 2, which you were pondering about previously, Kang, I think. Oh, I hear. I have this problem often in life. 2, we're supposed to calculate the integral over the unit 2 sphere, upper 2, of alpha. And, all right, so to do this, what we need is a parameterization of the 2 sphere. So the 2 sphere is given by x equals to cosine theta cosine phi, y equals to cosine theta sine phi. This is a different parameterization than the one you're used to, but it's There's a lot of different ways to parameterize a sphere, guys. So here theta and phi have their meanings reversed from what you're accustomed to. This is physics, theta and phi, or perhaps engineering. And here it's for, and he gives us ranges. He says theta is an element of minus pi over 2 to pi over 2. And we're going to let phi range between 0 and 2 pi. Now you might say that's not really the whole sphere, but he actually has some comments in this. By the way, this book that I'm looking at is Analysis and Algebra on Differential Manifolds by Gadea, Pedro Gadea, James. I can't say these names. Here, someone more educated, and anyone? Are you capable of saying these names?
Where is it? Oh, Pedro Gadea.
Pedro Gadea.
Jaime Munoz Masque.
Ihor. I don't know. These are I'm not trying to make fun of their names. They have done a wonderful masterwork in this book. It is a joy. It is a book of solved problems in manifold theory and so forth. It's extremely useful to me at times like this, when I'm looking for an example that's actually got some substance to it. But at the same time, it's not buried in the minutia of our current book. It's just like the core calculation. Okay, but what they point out is if you parameterized S2 up to a set of measure 0, which is basically to say up to, like, if it's a two-dimensional thing, if you're missing a curve on it, that's not going to change in integration. That's what we learn as we study more sophisticated integration methods like the Lebesgue method and all that. But okay, so getting to the point. The question is, what is alpha? So alpha restricted to S2, all right, is what? What that means is essentially it's essentially a pullback. I mean, you take the alpha over there, and then you plug in this x, that y, and that z, and work it out. Get rho equal to 1. It works out to minus cosine theta. It actually works out to minus cosine theta d theta wedge d phi. I feel a homework coming on. That seems like a homework problem right there, doesn't it? Yeah, it does. It does feel like homework. It feels like.
It's like if we say let f of phi theta give this x, y, and z, and then we say f star of alpha, then that would be what you
I think that would be right. I think basically this would, if we, let me write it down. So in terms of McNerney lingo, this is by definition, right, the integral of the pullback of alpha under the coordinate map to d, say. So these guys would be d, right? And f of theta phi is equal to that x, y, z up there. So the pullback of f under that is how we define the integration over this, of that alpha. Yeah. So anyway, what that means here is just we integrate from minus pi over 2 to 2, pi over 2, and we integrate from 0 to 2 pi of minus cosine theta d, I'm sorry, I did it, see what I did? So I got to put a plus there because I got to, sorry about that. Because I accidentally wrote down the phi range second. It's just me. Anyway, I could have written, well, I have to be careful. The ordering matters because these anti-commute. So,
but you can just switch those two integrals and get the sign.
yes, right. That would have been the same. Could have done that. And it's weird. Is that right? Okay, so this is, that's theta, right, this just gives me 2 pi, right? The, good grief, cosine theta d theta, right? Which gives me what, 2 pi sine theta evaluated from minus pi over 2 to pi over 2, also known as, well, 4 pi, right? Because we get a 1 from the upper limit and a minus 1 from the lower limit. So in total, we get 2 from that integration. And goodness gracious, I was supposed to get minus 4 pi. So I do have to be more careful about this. That minus matters, actually. I'm sorry, guys. So I can't just do that. That's wrong. I have to leave it. I'm so sorry. I have to leave that minus, and that's the rule. That's the definition. Is that I'm so sorry. It does matter because it's a minus 4 that we're supposed to get.
But regardless, if you kept the negative and you switch the dp and d theta, it still would still be minus 4.
Yeah, so how do you decide which order to put the dp and d theta in the first place?
But doing a double integral doesn't matter which one you do first, right? It's just a matter of what's easier.
Well, that's the thing, is the integration is taken over an oriented manifold. So the order of theta and phi matter.
So are they decided by the
If
way you have the nav?
if I put theta phi like that, then that means I have to have this as the oriented area form in the domain D. And so when I calculate the pullback, I have to, if I somehow calculated the pullback and it didn't come out to, for whatever reason, it came out to like d phi wedge d theta, if I'm saying theta is the first variable and phi is the second variable in the parameterization of the manifold, then I'm obligated to flip them so that they're in the right order.
So is this the inward one or the outward one?
I don't know. So sorry about that. So anyway, I'm sorry. Good grief. I will not go through that again. It works out to minus 4 pi, okay? Now, in part 3 was the interesting question, right? Why is it impossible for alpha to be exact on the deleted 3 space, on R3 with the origin punctured, removed? What would it mean? What is it? So if it was exact, that would mean that we could write, so let's go through it. Why is that impossible? So if alpha was exact, that would mean that alpha is equal to d beta on, R3 minus 0, right? So in particular, that would restrict to a potential form over the 2-sphere, right? And on the 2-sphere, we have the generalized Stokes theorem because it's a compact oriented manifold, so we can do there. On the, let's see here, on S2, alpha, well, that's equal to what? The integral over S2 of d beta. If it were exact, I would have that beta. And that would be equal to the integral over beta of the boundary of the 2-sphere. What is the boundary of the 2-sphere? Right. The boundary of the 2-sphere is nothing. There is no boundary to the 2-sphere. It's a closed surface. Closed surfaces have no boundary. So this being the empty set, this is 0. And yet, we just worked out it is minus 4 pi. We cannot have minus 4 pi as 0. So this is a very interesting 2 form for 3 dimensions with the origin removed. This shows that 3 dimensions with the origin removed is topologically different than 3 dimensions without the origin removed. Because this shows that there exists a non-trivial 2 form which is not exact. That would then go to that de Rham cohomology thing to show the existence of a non-trivial cycle. Well, anyway, let me not get into all that language, but yes, it is exactly because we wrapped a sphere around the origin. That detected there's a hole there, is the idea, roughly. Now I have the 2-dimensional version in the notes, right? We look at the x dy minus y dx one, but it's fascinating to me that this example is so telling about about the larger story of topology and everything, because it's also a physically, like, it's hard to miss physically. Like, this is the Coulomb field. There's hardly a more famous vector field than this one, you know? All right, I have one more integration to show you, then I'll stop with the integration. I'm going to shift gears after that example I have to show you. So I admit, like, I have not shown you enough to really sort out how to find the orientation, right? So you'll just have to be right, plus or minus, right? So you guys can at least form integrals up to a sign, right? It's pretty good. It's not bad.
It's either this or the exact opposite.
Yeah, I mean, you're you're either exactly right or exactly wrong, something like that.
Well, you just take the absolute value of whatever you get.
Just that, I used to do that in physics a lot. I'd be like, find the absolute value of the work done, because it's so fussy if you say work done by versus work done on.
I think you've asked us that.
So I will just throw in find the magnitude of the work, just so I haven't wrong.
You still get
I don't know which one is minus, which one is plus.
Yeah,
This throws around.
it'll drive you batty, no doubt. Okay, so this example, I found some fantastic notes written from some professor at Purdue, maybe 2015, and one of the examples in this just seemed perfectly appropriate for today, so I wanted to just share it with you guys because it's so nice. I will send you a link. I do not expect you to study this. It's a 50-page PDF, but it's about the level of this course, and it's written for engineers, and it's very calculational with a minimum of like mathematical rigor. It's not. Google. It's on the Google, yes. So what I'm going to share with you here is a calculation of the volume of a force sphere. So suppose you're looking at the set of x, y, z, t that is within distance 1 of the origin. That would define the so-called 3-ball. The edge of that would be the 3-sphere, S3, which is a 3-dimensional manifold in R4. And so you can ask, what's the volume of the 4 volume, which is inside that 3-sphere, and that would be given by the integral over that ball of the dx wedge dy wedge dz wedge dt. Now, to actually calculate that, you have to introduce coordinates or something, and so he chooses to introduce basically hyperspherical coordinates. He's even got a picture to justify it. Anyway, here they are. Here's your x, here's your y, here's your z. If you took calculus 3 with me, at some point I threw these on the board.
Did we do this like hyperbolic calculation in there as well?
We did, but not from the perspective of differential forms and with slightly different letters. But yeah, so you have 2 so-called polar angles, and you've got one that sweeps all the way around, and there's your radius. So when you pull back, basically, under this coordinate system, you get this thing, which works out to sigma cubed sine squared phi sine squared psi rather, sine phi d sigma, wedge d psi, wedge d theta, wedge d phi. And then you can integrate that over the appropriate ranges, and there you go. That's the volume of the sphere in 4 dimensions. The 4 volume enclosed by the S3, if you like, 1/2 pi squared r to the 4th. So, on the other hand, he says you could calculate using the generalized Stokes theorem. Now, this is very tricky. This is like in calculus 3, we do these problems where you calculate the area of some region by doing a line integral. This is just the analog of that. We're calculating a 4 volume by calculating a corresponding 3 volume. And the differential, see how this works? If you take the exterior derivative of that, you get dx, wedge dy, wedge dz, wedge dz. But then you got to move the dt 3 spots over to get back to that. So this is the exterior derivative of this is that. And that is the boundary of this. This is a set of x, y, z, t that is less than or equal to 1 in distance. This is the ones that are equal to 1 in distance from the origin. That's the edge of this guy. And so this is the generalized Stokes theorem. And then the question is, how do you actually calculate such a thing? Right? So what does that mean? You have to pick a system of coordinates on the 3 sphere, and then you pull this form back to the parameter domain of your coordinate system, and then you integrate by dropping the wedges. So the only thing exciting here, of course, is this t. What happens to t if you, I mean, what coordinate system are you going to use? I don't know. Well, let's find out. Here it is. So, oh, and by the way, you have to do upper and lower half to the sphere just like you would. I mean, so he looks at the upper and lower half of it, and anyway, and then he uses some symmetry argument to just double it up. But so that's what happens to the t. T in terms, so he's going to use x, y, and z as coordinates on S3 is what it boils down to. And in terms of x, y, and z, that's what t is on the 3 sphere. It's this pullback idea. It's exactly the pullback. It's a substitution of what t is in that manifold as it relates to the others. And then he just changes. Then he does integration. You know, he uses a rho phi theta substitution and gets the same thing. But I think this is kind of it's very pretty calculation. It gives you a non-trivial. I think it's very interesting because it shows you how we can use like generalized Stokes theorem to generalize some of the things you see in calculus 3 in terms of like swapping out area integrals for line integrals. You know, sometimes we could swap out a volume integral for a area integral or something like that too, over the appropriate thing, provided it's the right kind of volume. Generalized Stokes theorem does come with some fine print, right? It's only for like compact manifolds. So we have to have a manifold that has a boundary that's oriented. There's a fair amount of fine print that goes with the generalized Stokes theorem, but it's often applicable. So, all right, well, that's what I got for here. What's that? These minuses? I think it's because t is less than 0. So if t is less than 0 here, for example, then that means that minus t is actually the square root. On the upper side, it might be that, let's see, on the upper side, let's see here, dx, y, dz. Yeah, okay, so he's on the previous page just says that t is less than 0 for this one as well. I think that's, if that was it, that would explain it. Did that picture help you? 4-dimensional coordinate system? Yeah. Well, huh. because t is greater than 0 in the upper hemisphere, but maybe that's just a typo. That would be a typo. Would make a sense here. If t was positive up here, right? Then it would make sense. There might be a typo. I don't want to condemn the author of this without. But so this is Introduction to Differential Forms by very good. All right. So let us switch it up here and change change gears a bit. I want to talk to you now about a great mystery, which is why we use vector fields in Calculus 3. And I mean, how is it that we get away with using vector fields both as one forms and two forms, right? Why can we do that? Like, if you look at other dimensions, it turns out that that's not possible. I'll actually show you that explicitly here in a bit. But like, what's so special about 3 dimensions that allows us to look at one forms and two forms both as vector fields? It's a question you might ask, right? So it has to do with the binomial theorem, actually. See, because here's Pascal's triangle. These are the binomial coefficients that I'm writing down. That's also the dimension of the forms. So like this, if we extrapolate what this means in terms of the exterior algebra on R3, well, the exterior algebra on R3 is equal to 0 forms, direct sum 1 forms, direct sum 2 forms, right? Direct sum 3 forms. All right? And it just so happens that this has dimension what? Let's say d equals to 1. This has d equals 3 dimensions. This is a 3-dimensional vector space. This is a 1-dimensional vector space. If I'm thinking about forms at a point, right? If I'm thinking of form fields, then these are modules. All right. So I shouldn't talk about dimension. I should talk about something else, but let me not get into that. But, you know, essentially, what's our typical, we have a typical thing G here, right? Our typical thing here is our like work form correspondence, right? Our typical thing here is the flux form correspondence, right? And over here, we've got, you know, something like a volume form, f dx wedge dy wedge dz, right? These are the differential forms that we have to play with in R3. And it's just because that these are both isomorphic to R3 itself, right? That there is this interplay between these 3 things. They all have 3 dimensions, and they can be identified and interchanged.
So in general, in Rn, we can represent Rn minus 1, n minus 1 and 1 forms as vector fields.
Right. Yes. So if we're looking at R4, like this one, right? If we think about this as being the size of things in R4, so this would tell me that there's just, you know, you have functions, right? You have 1 forms that look something like, you know, But yeah, well, let me not start writing stupidly here. But yeah, they're apparently, if we think about R4, it can be either it has attachment to that and that. I mean, it's like R4 is the same size as 1 forms over R4, and also what? 3 forms, yeah. So 1 forms and 3 forms could naturally be identified with vector fields in some sense on R4. That's not entirely honest because they have different coordinate change properties, vector fields and forms. They have different coordinate change properties. But so this duality between forms of different degree that have the same dimension, right? This is called Hodge duality. So what Hodge duality points out is that at its base is this observation that if we look at P forms over V, these are isomorphic to N minus P forms on V. So here dimension of V is N. There's some kind of correspondence between P and N minus P forms. This is the Hodge dual. So like the simplest version of this would be something like the Hodge dual of the work form field. Guess what it is? And I'm going to get tired of writing that, so I'm just going to use a star, because after all, we haven't used star enough yet in here, have we? So star omega F is, but this is a big old fat star, so think of it as like a fat mid-placed star. That is, in fact, the flux form of F. That's the Hodge dual. That trades a 1 form for a 2 form. And the Hodge dual of a function is the function with dx wedge dy wedge dz. In R3, with the Euclidean metric. If the metric is not Euclidean, other things happen. But it's actually kind of fun. If you're talking about Hodge duality in with respect to the Euclidean metric, you can just kind of look at the list. Here, I can show you how to do it. If I have dx1 wedge dx2 wedge dx3 wedge wedge dxn, right? And I said, find the Hodge dual of like this. Guess what it is? Yes, it is dx1 wedge dx2. So it is literally kind of like, it's like the game you play with the snake and pushing it from one side to the other. It's kind of like, it's like whatever's left over is the Hodge dual. But it matters the order. So that somehow gets wrapped into this thing. So to define Hodge duality for a vector space that has a metric, and a metric I don't mean an inner product. A metric, so definition, if we have G that goes from V cross V to the reals, V is a real vector space, okay? And G is symmetric, non-degenerate, and bilinear, then that makes G into what's called a metric. Something called Sylvester's theorem says you can always choose a coordinate system which makes this look like basically a dot product, but possibly with minuses. So the example, I mean, there's basically 2 examples that I'm interested in. You could have G of xy equals to x dot y. For Rn, this is the Euclidean metric, right? Euclidean metric. But you can also look at, say, R4 with g of xy equal to minus x0, y0 plus x1, y1 plus x2, y2 plus x3, y3. In other words, this is the, well, the best way I know to write it would be, fine. Oh, x transpose eta y there in terms of a matrix. And this eta is minus 1, 1, 1, 1.
What is non-degenerate?
Non-degenerate means that the determinant of the matrix is invertible, which is a much weaker condition than like positive definite. For example, with this we can have a vector which with itself the metric gives us back 0, and yet the vector is non-zero. There are null vectors possible. For example, if you look at the vector 1, 1, 0, 0 here, it has g of that vector with itself being 0, and yet it's not the 0 vector. So it is not. Anyway, this is the Minkowski metric. And once you have a metric, so we getting to the point here, this g of xy you could write like this. This is really the sum x sub I, y upper j, g lower ij. So we can look at the components to the metric, g lower ij. And you can talk about g upper ij such that g lower jk, sum over j, I'm going to stick with the sums really quick here, Kronecker delta ij. And once you have this inverse metric, then you can start raising and lowering indices. We can start raising and lowering indices on forms and so forth. So, for example, just to get straight to it, because I don't have a lot of time, which is my own stupid fault. But here's the, for the, so suppose you have alpha equal to, like the sum over alpha I1, I2, IP, d dx I1 wedge dx I2 wedge wedge dxi dx IP. You could define alpha with upper j1, j2, jp. These are corresponding components, all right, to alpha. And the way this is defined is you lift the index of the alpha using use this inverse. Let me write down the formula. So g I1, g I1 j1, g I2 j2, g IP jp, alpha sub I1 I2 IP. So this is called raising the indices on alpha. It actually corresponds to using an isomorphism, converting alpha to a tensor